All right, ladies and gentlemen, welcome to the 11th day of the Ronco Show. Okay, so we are going to be, we have a number of items that we need to cover between today and our next lecture, because I actually have an interesting activity for us to work on during Flex, but I'm going to quickly talk to you, and we'll hit this back up again, on the second derivative, okay? We have been using the first derivative to find out where our maxima and our minima are. So just to recap, maxima and minima are found by taking the first derivative and setting it equal to 0. And those are the x values of my extrema. All right. If I wanted the y value of that extrema to actually find the xy point, whatever that may be, I would take that particular x and plug it back into the function to find out what its height would be. So let's do an example, okay, just for giggles. All right, let's do x squared, let's do x squared, let's move him over a little bit. And better yet, let's even do this. Okay. And what we're going to do is we're going to find the maxima and the minima, if they exist, and see what we can find. First of all, f prime, there's my notation for derivative, my first derivative. Using the power rule, this becomes 2x minus 8. Agreed? We're going to set that thing equal to 0, and now x is equal to 4. Okay, great. Now, to find out the actual honest-to-God point that I'm talking about, by the way, this parabola looks like this. Okay? In fact, actually, I lied. It doesn't look like that at all. It looks like this. The point, that because I know its y-intercept is -2. Okay? All right. So at 4 is my x-coordinate of my minima. And to plug it back in, I take 4, I plug it back in, I get f of 4 equals 4 squared minus 8 times 4 minus 2. So 16 minus 32 plus minus 2. So it's 16 minus 32 minus 2, which is equal to negative 18. So that point is 4, negative 18. Okay? That is the vertex. If you remember from Algebra 2 and probably HL1, when you dealt with the vertex form of a parabola, completing the square and all of that. And you might also remember, does anybody remember the formula for the axis of symmetry? Right. Why? If you ever forget the formula for the axis of symmetry, you can easily derive it. Any garden variety polynomial, any garden variety parabola, okay. The axis of symmetry is where the minimum or maximum is going to be, right? That's the vertex. Your derivative is 0. So f prime of x is equal to 2ax plus b. And then we solve for 0. We set it equal to 0. That's what, that is the equation of symmetry for a parabola. And that's why it is what it is. So there's actually a guy who sold Jack his beanstalk beans. Okay, I mean, this stuff is not magic. It comes in the process of hunting down an answer. All right, great. Well, this is wonderful and all, but what if I didn't have a graph? And I wanted to find out if this was a minima or a maxima, okay? Well, let's look at the second derivative. The second derivative means I take my function and I derive it. I take a derivative, and then I take another derivative. I take it twice, okay? And that would be this is written this way, okay, in terms of that notation. In terms of Leibniz notation, it looks like this. Well, let's do it correct. What I'm doing now, this is not what you would write every time, but in fact, this becomes this means the second derivative. And sometimes you'll see that y written up top. Okay? This represents the second derivative with respect to x. All right. What the second derivative curvature. And it tells me curvature. There are two ways that you can be curved. Well, besides 0. You can be positive curvature or negative curvature. If my second derivative and I should say is greater than 0, if it's a positive second derivative, all right, that means that I am curved concave up. If I am negative, then I am concave down. So if I'm concave up and I'm at a minimum, sorry, and I'm at an extrema, I know that I'm dealing with a minimum value. So, well, I should say that if the second derivative is 0, what do you think that is? Yeah, it's a constant. It's a constant curvature, which means it's got a horizontal. Um, Now, there are some funny things that go on in here. Actually, I shouldn't say 0 curvature. I should say constant curvature, because it doesn't have to be 0. Oh, yes, it works for all functions. Okay. All right, so let's go back to my parabola example of this fellow. All right. And if I take my second derivative of that guy, my first derivative, and then my second derivative, okay? And now when I plug in a value into that, it still is 2, which is greater than 0. So that means I am concave up.
You forgot to add the two dashes on top.
No, no, I didn't. Wow, you guys are picky. No, it's all right. It's cool. Yeah, it's fine. That's good. All right. So with this, we could find all of our maxima and all of our minima. All right. And we can find out if they are, you know, curving up or curving down, and therefore determine if they are minima or maxima. We can find the extrema with the first derivative, and we can find the curvature with the second derivative. And grand total, that means that we can find out everything about it. No, f double prime. F double prime. Okay, we'll just call you double prime from now on. Okay, that's it. Okay. All right, so okay. So now you guys can play with this one. That's good. That's enough for now. And so these are the locations of my two extrema. Okay, those are, you know, that is where you have to understand what you're looking at. You're looking at the places where the slope is 0, right there. Okay. Now, to find my curvature, that's 6x plus 4. Now I take those two locations and find out what is going on. I'm going to plug them both in. So I get f double prime of 0 is equal to 4. Okay. And when I plug in the other fellow, negative 4 thirds, that gives me 2, negative 8, positive 4. Right? Is that true? Negative 4, negative 8. No, negative 4. I'm sorry. Right. Tells me right here, this guy is a positive curvature. And if I have a positive curvature, what does that tell me about this guy? That it's a minimum. And this guy has a negative curvature, so he is a maximum. All right. Now, we do not know if they are absolute or relative maxima, but inspection, you can do that. You know, just by looking at the picture, you can find out if they're extrema, if they're maxima or minima. But it's a cubic, right? So what are the extrema for a cubic? The absolute extrema for a cubic. Yeah, positive and negative infinity, because you're going to have something that looks like that, right? Okay. What? Sorry? These are relative minima and maxima. They're this fellow and this fellow. And if my people on YouTube don't mind me switching off for a hot second, I will. You'll be able to see this on the smartboard, but you're not going to see this on the video. Can someone read off my equation, please? It's x to the third, right? Yeah. I really don't like this new operating system. Plus, what was it? 2x squared. And there you can see that I have a local minimum at 0, right? And I have a local maximum at negative 4/3. Okay? Are we cool? All right, great. All right. Right. Okay, great. So the second derivative gives me that information, which is quite useful. Are we cool? Under control? All right. Chain rule. Chain rule is really, really, really useful. Okay? The chain rule allows me to take really ugly looking stuff and take derivatives of it, composite functions. Okay. For example, if I wanted to find the derivative of, say, if I wanted to find that, ooh, Ronco, that's no fun. In fact, it's actually a lot easier than you think. Yeah, I could expand that whole polynomial out and then do the product rule. No fun. I don't want to do that. That's why I gave a problem like that for you to do on your homework. Yeah. Yeah, right. It's a mess. But it's not impossible. And in fact, what we can do is we're going to make a really nice substitution. This is a really simple way of making nasty stuff come out really nice. So now this becomes very simple. And I can take the derivative of that in my sleep. So can you. Well, but that's not really what I'm trying to find. So let me get my notation right. This would be, and actually, if you don't mind, I'm going to go back to y for a hot second. This would be dy, sorry, then y is this, then dy du is 3u squared. I'm taking it with respect to u. U is the thing that is changing in this, yes. Why? This is being recorded. We're good. So, right. So one thing to note is that you have to get the notation right, dy du, because I don't have any x's anymore. Okay? But u is a function of x, right? Just like in this case, y is a function of u, here, u is a function of x. So du dx is 2x plus 3. Done is I've taken this guy apart into pieces and played with the two pieces. One piece is the outer wrapper, in a sense. It's that cube, okay? If I were to walk up to this function, if I were to walk up to this guy on the sidewalk and pick him up off the ground, the outermost thing that he is a power, okay? If you think about it as in the concept of, say, layers of a box, like a Christmas present, okay? On Christmas, birthday, whatever it is, when you get that present, you must first take off the paper. It's the outermost wrapper. Then you have to open up the box. Then you have to remove all the stuff inside. And then you have the present inside, okay? You have to go from outermost layer on in. That's what we're doing here. We're looking at the outermost wrapper as a cube. And then the innermost piece is actually a sum. It's a sum of an x squared, which is a power, and 3x, which is a multiplication. Okay? Now, we have these two. So what I'm really looking for is the derivative of y with respect to x. And here's how we do it. And this is why Leibniz notation is so powerful. If you'll notice, that is my dy du, but I've resubstituted, times du dx. All right. Okay. So when you do this, you have to take, it's the same idea behind that wrapper. May I go past this? You see, when I do this step, I go from the outermost wrapper. The outermost wrapper is that exponent. I unwrap that exponent, which means I take a derivative of it. That 3 became a 2 and and came down in front as a coefficient. When I take that wrapper off, what's inside the box has not changed. It's only when I get past that layer that I can fool with the stuff that's inside it and take a derivative of it. Okay? So, let's try this. Green pass. Let's do all right. So, the first thing I fool around with here is you have to look at this and say to yourself, what is the outermost wrapper? The outermost wrapper is a square root. So when I, quote unquote, unwrap that, when I take a derivative of that square root, it becomes you guys remember from the other day when I take a square root of a radical? Not negative. when I take a derivative of that, the 1/2 comes down, and I subtract 1 from my exponent. It shouldn't be negative. That's what everyone was complaining about, right? Yeah, Bronco. Sure. And this becomes, so the derivative of a square root, it comes down below and you put a 1/2 out in front. All right? There are some derivatives that you're going to need to know cold, and this is one of them. So if in this case I let u equal x squared minus 4x, right? So when I do this, I first unwrap the square root, and when I unwrap the square root, what's inside the box hasn't changed yet. Now, since I've done my outermost wrapper, I can now take a derivative of the inside of the box, which is this fellow. Do you understand this analogy, what I'm talking about? When, like outermost layer, innermost layer, and so on and so forth? Yeah, you first deal with whatever's outside, then you fool with what's next, and then you keep going in like those Russian dolls. You know what I'm talking about? Where one is stuck inside another, which is stuck inside another. This is y prime. And now we can simplify. Okay. So we're going to, yes? I didn't need to, really. I mean, writing out this whole steps of the chain rule. The chain rule is truly this. This is the chain rule. That's the chain rule. And in fact, it can be even bigger. You can have multiple layers. If you think about a Russian doll with more than just one guy inside, if you had like 3 different layers, you could blow it up that way. And that's the idea. You do the outermost layer, then you multiply it by the next layer, and then you multiply it by the next layer. Each time that you do it, what's inside it doesn't get changed yet. And you just kind of go down the line, okay? Now, I am going to do something with this class that I haven't yet done. I'm going to put you all on the boards. Oh, that's right, very first day. Hit the boards, people. I'm going to pause the Ronco show for a commercial break. Okay. So now that we've done some board work, here are some absolute derivatives that you really, really, really need to know. All right. Derivative of sine is cosine. Derivative of cosine is negative sine. The derivative of tangent is secant squared. Guys, please. The derivative of cosecant is negative cotangent cosecant. derivative of secant is tangent secant. And tangent is negative cosecant squared. Those are the trigs that you need to know now. Make sure everyone has that before I move on. Yeah. Yeah. No, that's just, and I'm going to go into that next. All right, does everyone have these copied? Waiting for pencils, waiting for pencils, pencils, pencils. Awesome. Of log base b of, so any base, 1 all over x times the natural log of b. You will see natural logs as the logarithm of choice in calculus. And if we have time, we'll do that next class or during flex. We're about to run out of time here, but and because of this, because of the natural log of e is equal to 1, that means this b. You see, here, if I take the derivative of e to the x, I just get, my base is e, I get e to the x, ln of e, which is 1. So this function, the derivative, is itself. Yes, yes, that's exactly how I felt when I found out too. I was just in awe. This episode of the Ronco Show has been brought to you by the second derivative and the number 4.